Good afternoon, everyone. So today we have the lecture three, and in the previous lecture, what we have discussed about some of the isomerism, what kind of isomerisms are present in the organic chemistry, structural stereoisomerism, and some of the nomenclature of organic molecules, some of the functional groups, and how it's the priority order increases or decreases in the nomenclature. So today we'll little bit start from this organic reaction mechanism. Okay, so let's say if we consider one organic molecules, then if we consider one organic molecules, then let's say some attacking reagent, it's coming from outside. Okay, attacking reagent coming from outside, and we'll end up getting what kind of thing? One intermediate. Okay, now this intermediate which represented in this third bracket. This is third bracket. Then here two product formation. One is the product, whatever we are expecting, the product formation, and as well as plus another byproduct also may generate here. Okay, byproduct also may generate. So in general, this organic reaction mechanism is going via two way. So two way is the organic. So we'll go one by one. So let's say it is a organic reaction, and it is going via two way. One is the homolytic cleavage, and another one is the heterolytic cleavage. So one is the homolytic, and the second one is the heterolytic cleavage. Okay, so these are all covalent kinds of reactions. Covalent bond breaking and making happens in the reaction mechanism. Covalent bond. Okay, it's all about the covalent bond. Now we'll go little bit about the homolytic cleavage and the heterolytic cleavage. Okay, so we know about this homolytic cleavage. So let's say now this covalent bond, how one can go this fission of this covalent bonds. So one is the homolytic, as I say, homolytic, and the second one is the heterolytic. Okay, heterolytic. So we'll go one by one. So what is homolytic? So no, first we'll discuss about the heterolytic. So this is the most important topic in the organic reaction mechanism. So what is heterolytic? So let's say heterolytic cleavage, how it happens. Okay, so heterolytic cleavage, let's say after heterolysis in this reaction, let's say if we consider one reaction mechanism, and after heterolytic cleavage happens, so one atom has one atom has a six state type electronic structure. Electronic structure. Okay, and positive charge, and it will bear a positive charge. It will bear a positive charge. Okay, positive charge. I'll come to the example. First, let me finish this one. And the another one will be the other atom will be the valence octet. The valence octet. Okay, with valence octet with at least one valence octet, at least one lone pair, and negative charge. Okay, now if we, let's say for an example, if we take an example, let's say we have CH3 and Br. Okay, that is known as the methyl bromide. This molecule name is methyl bromide. Okay. So how this happens? So let's say if it is goes via the heterolytic cleavage, if it is happen the heterolytic cleavage, then you will end up getting CH3 plus plus Br minus. So as I said, one atom has a sextet electron because CH3 carbon, this is a carbocation moiety, okay, and this is a carbon ion moiety. This is this is a negative anion. This is a Br minus. So this is, I already said that the atom, one atom has a sextet electronic structure. So carbon and CH3, this is a sextet electronic structure. Okay, electronic structure, and this is the octet, and at least octet and one negative charge. Okay, so this is how the heterolytic cleavage happens. Now we'll discuss, so in general then what will happen. So let's say go to the next slide. So we'll start from the, now we'll discuss about the uh, methylium cation. So carbon atom possessing sextet of electron and a positive charge is called. So what we see, what we have seen in the previous slide, the carbon atom is bearing a positive charge, a positive charge, and sextet electronic structure, sextet electronic structure. So that is why the CH3 plus is called as a carbonium carbocation. So this is called carbocation. Okay. But in earlier days, what people are called as a, earlier days, people are called as a carbonium ion, because it is a ion, it is not a neutral species, so that is why it is called as a ion. And why it is carbonium, as it is a positive charge bearing CH3 plus, this is a positive charge bearing, so that is why it is known as the carbonium ion. Okay, so now, and also it is also known as a carbocation. As I said, this is also, this is known as the carbocation. This is also another important part of this one. So we'll discuss about the carbocation. So what kind of carbocation it is present in the organic molecules or in chemistry. So let's say CH3 plus, so we have the CH3 plus, then what is the name of this molecule? So we can say this is a methyl carbonium ion. Okay, carbonium, methyl carbonium ion. Okay, now we'll discuss about the what are the stability of this carbocation. So first we go to the stability, the carbocation, the carbocation stability. Okay, carbocation stability, carbocation stability. If we discuss about the carbocation stability, then the lowest priority will be the CH3 plus. Then the next one will be the ethylene cation, CH3, CH2 plus. Okay. Then the another part will be the CH3 whole to isopropyl cationium plus. Okay. And the most stable one is the CH3 whole 3 C plus. Okay. So this is the most stable carbocations. So these all are the carbocations, moiety. Carbocations. Carbocation. And among all them, this is the only one, CH3 whole 3 C plus. That is, you can also write like this way, CH3. Okay, CH3, and this is the CH3. So this is the one, the highest priority. Then the second one is the CH. So another CH3. So this is the second priority. Then the third one is the CH2. Okay, CH3. And here only one CH3. Okay. So this is the lowest one. This is the lowest one, and this is the highest one. Most stable carbocation. Now, now we'll discuss about the. So what are the stereo hybridization of this all these carbocations? So you can see all the carbocations are, always remember all the carbocations are sp2 hybridized. sp2 hybridized. Okay. All the carbocations are sp2 hybridized. Okay. Now the next slide. In the next slide, what we'll see. So the sp2ch, let's say carbon sp2 sp2 hydrogen, and this is a 1s. So what kind of bond formation happens with CH bond? So carbon will use this sp2 orbital and hydrogen will use the 1s orbital. Okay, then it will form a sigma bond. Then it will form a sigma bond. Okay, now this sigma bond, the remaining carbon orbital is the remaining carbon orbital, the remaining carbon orbital is perpendicular to the all the orbital. Remaining carbon orbital is the perpendicular to the molecule. Perpendicular to the molecular plane. Perpendicular to the molecular plane. So what if we see the structure of this molecule, perpendicular to the containing no electron and also containing no electron. Okay, containing no electron. If you see the structure of this molecule, so let's say this is a hydrogen molecule, this is a hydrogen molecule. So we are talking about methyl carbonium species. Okay, so and this is the one that where you will end up getting this methyl carbonium cation. So this is called methyl carbonium cation. Okay, methyl carbonium cation. Methyl carbonium cation. So where all the CH bonds are making a sigma bond. This is a sigma bond. This is also sigma bond. This is also sigma bond. So all the sigma bond are perpendicular to the this perpendicular to the carbon orbital. Now we will discuss about the heterolytic cleavage can also gives a. So far we have discussed the in the heterolytic cleavage, in the heterolytic cleavage, in the heterolytic cleavage the heterolytic cleavage, carbon contains the positive charge. Carbon bears a positive charge. Carbon bears a positive charge. Okay. So if the reverse case can happen, yes. The answer will be yes. So in first part, what we have seen, the carbon are bearing in the positive charge, right? This is the positive charge, and the another negative addendum is also generated in this heterolytic cleavage. So the opposite case also happens. How? So carbon can also maybe act as a anion, carbon ion species. So how it will happen? So let's say if we take an example CH3 and any molecule, let's say Z, then if this all the sharing of electrons comes to the CH3 group, then what will happen? Carbon bearing a negative charge. What will happen? CH3. Okay, this is a negative charge, and what will generate? J plus. So now this anion, carbon atom bearing a negative charge on carbon cation, a carbo atom. So this is called carbon anion. So what we have seen, when the carbon bearing a positive charge, this is called carbonium cation or carbocation, or if the carbon bearing a negative charge, then it is called as a carbon ion. Okay, it is a negative charge, then it is a carbon ion. Now the organic reaction which proceeds heterolytic bond cleavage are ionic or heteropolar or just polar reaction. Okay, so if a one reaction, so if a reaction, if a organic reaction, if a organic reaction proceeds, okay, proceeds, organic reaction proceeds through a, organic reaction proceeds through a heterolytic bond cleavage, heterolytic bond cleavage are always ionic, are always ionic or polar, are always ionic or are ionic or just polar reaction. Now we'll go to the next part of this organic mechanism, that is the homolytic cleavage. So what is homolytic cleavage? Now we'll discuss about the homolytic homolytic cleavage. Okay, homolytic cleavage in organic reaction, in organic reaction. So in general, these homolytic cleavages are gone through via in homo in homolytic cleavage. The so what will happen in after homolysis, after after homolysis, after homolysis, movement movement of a single electron, movement of a single electron takes place. Single electron takes place. Single electron take place instead of, okay, instead of electron pair. So what we have seen in the heterolytic cleavage, the electron pair movement happens. Electron pair movement happens in the heterolytic cleavage. But in homolysis cleavage, what will happen? The single electron, only the single electron movement will happens. Okay, so we'll go to the example. Let's say if we consider an example, let's say Rx. Now if this Rx homolysis cleavage will happen, then this it will generate, it will go by this half arrow. One electron will go to the X and another electron will go to the R. Now it will generate R dot and plus X dot. So dot means, so two electron is form a bond where these two electron share by two different atoms. So one electron goes to R and the another electron goes to X. So in this way homolytic cleavage happens. Now this R act as a free radical. Okay. So whenever you will see any atom bearing only one electron, then it's act as a radical. Okay. So if R is a carbon, then it will be a carbon radical. Let us say now we'll see the stability of the allyl radical. So let's say if we start from the allyl radical, okay, so this is a alkyl. So we are talking about the alkyl radical stability, how it depends. Alkyl stability order, alkyl radical stability. So if you see the alkyl radical stability, so the first the less stable will be the methyl radical CH3 dot. Then it will come the CH2 and CH3 dot, that is ethyl radical. Okay, so this carbon dot will be in CH2 carbon. Then the compared to ethyl, isopropyl radical will be the more stable. Isopropyl isopropyl radical will be more stable. So what is isopropyl structure? So that is CH dot and CH3 whole 2. That is called isopropyl radical. Now the third one, the last one is the which has the most stable conformer. That is the tertiary butyl one. That is CCH3 whole 3. That is the tertiary butyl radical. Third butyl radical, or in short name we can also say that this is third butyl radical. This is the highest stable, highest stable radical. This is on the, and that this one is the least stable, means less stable. So in organic reaction, which in general, organic reaction proceeds, organic reaction which proceeds by homolytic reaction, by homolytic, that means by homolytic fission, that means in general as a called as a free radical or non-polar reaction. So that is a free radical or non-polar reaction, free radical or non-polar reaction, or non-polar, free radical or non-polar reaction. Okay, and also you can say the homopolar reaction, homopolar reaction. So now we'll proceed through the nucleophiles and electrophiles. So we'll next we know about the what is nucleophiles and electrophiles. So one by one we'll go. So in nucleophile what happened? The nucleophile. So what is nucleophile? So nucleophile is a reagent that brings an electron pair, that brings an electron pair, that brings an electron pair. Okay, is called nucleophile. It's called nucleophile. Okay, now nucleus seeking reaction is called as a nucleophilic. Nucleus seeking reaction is called nucleus seeking reaction, is called nucleophilic reaction. Nucleophilic reaction. Okay, now for we'll come to know the then what about electrophile. So what is electrophile? Okay, now we talk about the electrophile. So what is electrophile? So electrophile is the a reagent that takes away an electron pair. So what is nucleophile? So nucleophile is a reagent that brings an electron pair, is called the nucleophile. And what is electrophile? The same opposite to the nucleophile. So what is the opposite? The a reagent that takes away the electron, that takes away that takes away the electron pair, takes away an electron pair, is called electrophile. Okay, so now we'll talk about some example of the electrophiles and nucleophiles. So let's say for an example, we'll talk about the HO minus, that is hydroxide ion, hydroxide, and that is Cn minus, that is cyanide. Okay, cyanide, and some of the carbon ions, like carbon ions means carbon bearing a negative charge. So that is Cr3 minus, that is carbon ion. Okay, so these are all not neutral compounds, not neutral groups which can act as a nucleophiles. So now we'll talk about some neutral molecule. They can also act as a nucleophiles. So some, if we talk about some neutral molecules are like water can also act as a nucleophile. So water, H2O, R3N, and R2NH. This kind of amine, this is a tertiary amine, this is a secondary amine, you can say. So etc. can also act as a nucleophiles. So they can also act as a nucleophiles. How? Because of presence of their because presence of uh, lone pair of electron. Lone pair, lone pair of electron. Okay. Now we will talk about the electron movement in organic reaction. So how the electron movements happens? Electron movements. If we talk about the electron movements, then how electron movements in organic reaction? In organic reaction. Okay. So how the electron movements happens in the let's say foreign reaction mechanism. So if we consider a simple example like this one, one double bond Y and one single bond. Now if this electron movements happens, now let's say this double bond will shift to this single bond. Now it will, what will generate? This double bond comes a single bond, and the single bond comes to a double bond. So from 5 bonds to adjacent bond position. Okay. Now B. What about B? So B is Y and the single bond. Now the from pi bond to adjacent atom. From pi bond to adjacent atom. Then what will generate? Y dot and Y. That is from pi bond to adjacent atom. So in previous case, what is happening? So pi bond to single bond position, pi bond to another single bond, sigma bond. But here it is going a pi bond to an atom. So that is why from pi bond to an adjacent atom. Now the third one is the, let's say Y, one lone pair is present, and then how this electron movements is happening. So from adjacent atom to bond. So that will be 1, then Y, then double bond. So that is atom to atom to adjacent bond position. Adjacent bond position. Okay. Now, if we take an example, let's say we have HO minus. In first case, we have discussed about HO minus, that is hydroxide, can act as a nucleophile. Now we have another molecule, that is CH3Br, the methyl bromide. Now this OH minus act as a nucleophile, and it will come and attack to the electrophile. So which is electrophile here? CH3, because CH3 is attached to a most electronegative atom. So obviously CH3 will be delta plus, and this negative nucleophiles is coming and attacking to the one electrophile. So obviously in organic reaction we need one nucleophile as well as one electrophile, so that nucleophile can go and attack to an electrophile. Okay, now this OH minus is attacking to a CH3 molecule, and what we are getting? CH3OH, that is nothing else, methanol plus Br minus. Okay, so this is going via heterolytic cleavage. Heterolytic cleavage. This reaction is going via heterolytic cleavage. Now, if we talk about the another example which is going via homolytic cleavage, let's say we have CH3Cl. Now this CH3Cl, one single bond is always formed by two electron. So this two electron is shared by both two atoms. Now what will generate in homolytic cleavage? CH3 dot plus Cl dot. So that is the homolytic cleavage. Okay, homolytic cleavage.